Hello and welcome to today's daily Leetcode challenge. Today we'll be solving question 332. I'll be going through my thought process as I come up with a solution. At the end of the video, I'll compare my solution to the solution of others on Leetcode and see where I could potentially improve it. With that, let's begin question 332, Reconstructing Itinerary. So, you're given a list of airline tickets where ticket I is from to, representing the departure and arrival airports of one flight. Reconstructing itinerary in order and return it. All of the tickets belong to a man who departs from JFK, thus the itinerary must begin with JFK. And there are multiple valid itineraries. You should return the itinerary that has the smallest lexical order when read as a single string. For example, the itinerary JFK LGA has smaller lexical order than JFK LGB. A lexical order just means that the characters and in the ASCII characters, there's a lot of them, but you can compare them. Lexically, A is greater than B. And so in order just means that A precedes B and so on. Very obvious. You may assume all tickets form at least one valid itinerary. You must use all the tickets once and only once. Okay, so... question in my own words. This is asking us to, given essentially a number of flights, we have to reconstruct a valid itinerary. Itinerary just means the flight path taken from JFK to some other airport, such that we use up all the flights. And if there are multiple itineraries, then the one lexicographically smaller will be the correct one. So this question seems right away like a graph problem, where we essentially maybe have a modification to the deep first search algorithm, where we figure out which depth, because there could be multiple. JFK could have been pointing to Munich, LHA, SFO. We figure out which one of these airports we have to take in order to come up to a valid DFS dive. DFS algorithms always need like an intermediate data structure, usually just called an adjacency array. In this case, it's probably just going to be something different. But we need an adjacency array and a modification to the DFS algorithm to figure out which of its neighbors that we should proceed with. And I'm actually just going to start with the implementation now. Let's see. The implementation. So we need the adjacency array. Adjacency is going to just be a default dict with a list as its default value. We need for, from, to, and tickets adjacency from append to. When I print it, you will see that we have a populated adjacency dictionary. Now what? Now we need a modification to we need a DFS algorithm and a modification to it. As we know that we start from JFK, I'm going to list JFK as the definite first starting point. And now what? Well, now we have to basically iterate over all of possible neighbors, right? So for 2 from 2 in adjacent from, I'm going to say basically, so under which condition do we, and this is the way that I like to think about it, under which condition do we proceed with a neighbor? Well, first let's consider this neighbor. And to consider this neighbor, we have to do a couple of things. Actually, I'm going to say I and enumerate. I'm going to be iterating over the possible over the possible neighbors, right? So what would I do here? I would say adjacent from pop I, res append 2. This is me considering this this potential neighbor as a valid path. I've added it to my result and I've popped it from the adjacency array. Makes sense, right? So now I consider this, meaning that I basically just say if DFS with my new from, then return true. What does this mean? If I have successfully traversed or dove deep into DFS with 2 being equal to true, that means that I'm a valid 2, essentially. If we dove successfully to DFS with a valid 2 that actually is a from, then we're a successful from. If not, I'm going to revert this mistake, and reverting the mistake is the adjacent from insert into I2 and res pop this. Then obviously if all of this didn't pass, then I return false. And what else, under which else condition, under what conditions do we also potentially want to return false or true prematurely? I would say that if we are done, if we've completed or exhausted the adjacency array, and we can actually do that very simply. We don't have to look at what the adjacency of the length of the adjacency values are. We can simply say that if len of res is equal to len of tickets plus 1, return true. That means that we've successfully went through all of the itinerary. We've successfully constructed an itinerary. And also there's another situation where from is not in adjacency array. Also return false. So given that we have this modified version of DFS, let's call it with JFK being the first value, and return res. Submit this, and we get a correct answer for the first one, but a wrong answer for the second one. So what I'm guessing is I did not sort the incoming because it has to be lexicographically correct. Let's actually just sort this. Tickets sort. Yeah, I'm a bit on a tight schedule, but let's see. Cool. Let me explain what actually happened here. Printing by actually printing. Let's print before and after. tickets print. Let's see, will we get it for the second example? I think we should. So, as mentioned before, lexicographically in order strings are those where characters are also in order. And what would happen in this case is if two input, if two values are almost identical, for example, JFK SFO, I would, let's see, JFK SFO has to come after JFK Atlanta. JFK Atlanta comes before JFK SFO. This is a Python specific approach. In other languages, you might have to physically or manually sort the input arrays, but since here it's essentially like the comparator destructs the array and compares everything, it's easy enough to simply do a sort here, which would mean that eventually when we are considering our neighbors, we are considering them in order from lexicographically smallest to the lexicographically largest. Okay, so yes, as mentioned before, we first construct this adjacency data structure, adjacency dictionary, and then modification to the DFS algorithm. Pretty simple. Okay, let's look at improvements that we can make. And yeah, this I guess is not the fastest solution by any means, but look, the solutions here also use a DFS algorithm. They also use the adjacency array, so pretty correct. Interesting. So here, the DFS algorithm seems a lot less how to say it, important. It simply looks to see that while the adjacent of a specific node has a has any sort of values, it's not empty, then destination is going to be adjacency node pop last. I see why they're doing pop, because popping is better than going from the beginning. And then calling DFS once again. Default tickets sorted. Okay, but I'm confused about this. For I and j, for from to in tickets, first populate this array, which makes sense. But then for key in adjacent, you sort by what? Oh, sorted adjacency key, but we can do that way easier. And then but then how do they know that you have successfully dove deep into a correct dive when doing DFS? That's what I don't understand. This part is clear as day, but maybe the structure, the structure of the adjacency array where it's reversed enables us to lexicographically pick the smallest destination first, which is fine. We pick it, and then yeah, how could this not just accidentally go into a, oh, I guess, is there no chance that it ever goes into a, like an incorrect itinerary? Let's try that, I guess. Um, let's try the same approach. We have an adjacent C array that is just default uh, default dictionary of type list for FRM2 in tickets. I'm going to populate the adjacent array FRM append 2. Then I'm wondering, can I do this in reverse? Can I, instead of sorting each of the, no, see, I can't sort each of the, I can't sort in reverse order the input ticket array, because here we really have to sort the to destinations, not the from destinations. And so unless I sort in reverse by a specific key, which I could do, let's try this. Tickets sort key lambda x x1 verse true. True. Can I do this? Oops. Add. Oh. And so I'm seeing, is this correct or not? BC L M N O P Q R S and then S T F F J. Perfect. This worked. Okay. So now that I have this reversed, let's see. Can I simply populate my from and the twos? Print adjacent. This is getting maybe a bit too complicated. But my computer's gonna die. I'm really rushing. Let's just see if maybe we can, say, steal, but borrow some of this code with slight modifications. Okay. So this is the adjacency array. We want the adjacency to be sorted reversed true. And then we want this. We want to return res. And then we want actually want to do this before. And while res DFS of JFK, while node adjacency node pop. So does this work? If not, I actually would probably have to. Sweet. And my computer died as soon as I pressed that button. But yeah, this is what we ended up on. A modification to what is said to be the fastest approach. Um, the modification here is that we don't reverse each value individually, but rather sort the input tickets array by the destination. Yeah, I'm still not entirely sure how to visualize this in um, without maybe without a drawing, but the intuition here is that um, reversing the incoming tickets array by the destination gives us a order of tickets that starts with the lexicographically, basically a reversed tickets array by the lexicographically destination. It's graphical destinations. And then when you are considering those, when you're appending to uh, to the from to the key values to the neighbors of the adjacent key, you are reversing it back into it being, let's see, what's a good way to show this? Print adjacent. So tickets used to be in the reverse order, but now all of a sudden they're not. They are now once again. Is there even an example where yes, there was one here. JFK, SFO, JFK. See, so JFK, SFO. The two. Wait, am I even correct? The two? I think I'm confusing myself. Um, I like the original solution, to be completely honest. I was just trying to get get it a bit faster, but yeah, sorry for the confusion. Use whichever one you like. I like less code, but I also like more intuitive, more readable solutions. So, yeah, thanks for watching and see you later. Bye.